Andrew is our next speaker, and is going to tell us about how to fill type holes with large language models. Very exciting. Future of programming.
All right, hi everybody. I am here today to talk about statically contextualizing large language models with typed holes. And this represents work done by myself, Andrew Blinn, as well as Kevin Lee, Jacob Kim, and Cyrus Omar, all of us at the Future of Programming Lab at the University of Michigan. So, as most of us know, LLMs often produce broken code. And sometimes this is due to deeper, more intrinsic issues, but often it's due to the fact that they lack appropriate code context. So, how can we best provide context to inform LLM code completions? Our approach is a kind of conversation between programmer, language server, and language model using typed holes to bridge cursor local and repository-wide semantic information. We implemented our method in Hazel, our lab's typed functional programming language and live program sketching environment. We chose Hazel because it has many features supporting such an investigation, and we were interested to see if we could use contextualization to get higher quality completions in a low resource language, so a common theme with the last talk. That is one not well represented in LLM training data. We also reproduce part of our method in TypeScript. Now, I'm going to switch over briefly, and I have to do a little bit of display juggling here, so apologies for that. I'm going to mirror and switch to the Hazel editor. And so yeah, this is the Hazel editor. And one application we've been investigating with Hazel is the development of GUI apps, in particular apps in the Elm architecture or model view update, MVU tradition. And what you see before you here is a program sketch of a simple to-do app. And to define an MVU app, you specify a model type, which is the application state. You specify an action type, which are the user actions that you can perform. And scrolling past some helpers here, we get to the update function, which defines the core logic. That's a pure function that takes a model and an action, produces another model. And scrolling past some more view helper functions here, we get to a stubbed out view function here. And Hazel is a live program sketching environment. And that means, among other things, that if you select this typed hole here, in the body of the view function, you see down below the expected type that we need to fill that hole with. Also over here, you can access the typing context. So this gives us a list of all variables that are in scope at that hole, along with their types. And previously in Hazel, we've used this information to support a token-by-token traditional type-directed auto-completion process. But what if you want something a little bit more interesting, a little bit more creative? So you might notice in this comment up here, I've specified some perhaps questionable design decisions as to what the view function should look like for this application.
Can you switch the side?
Yes. Okay. Oops. Sorry. All right. Can you hear me? All right. Okay, so I entered question mark, sending off a request to the language model for a code completion. Something's come back. I'm going to press tab to accept it and scroll down to the bottom. And yes, in fact, we now have a super duper to-do app right here. And I think this looks pretty nice. So I'm going to say, I don't know, maybe improve color and add a to-do. And I'll come back to that later. But anyway, I just like to show this kind of example because I think as programming language people, we're reluctant, justifiably reluctant to kind of put these big, opaque, black box, weird processes like in our core business logic, give them access to the levers of power. But sometimes what we want to do is just kind of move off of the blank page and get something to iterate on. So switching back to the slides, and again, bear with me here. Stopping mirroring. And we're back. Okay, great. So yeah, that's some other variations which I've gotten with the similar prompt there. To motivate our problem in a little bit more detail, as a running example, we're going to consider another MVU app, Emoji Painter, which is going to allow the user to stamp emojis on a grid. The language model's task will be to complete this sketch of the app's update function. Now, consider trying to complete this sketch yourself. Similar to a language model, deprived of context, you'd have little choice but to hallucinate a completion. Now, prompting an LLM is sort of like trying to quickly onboard a developer who has a large amount of shallow knowledge. So similar to posting a question to Stack Overflow, the quality of the response is going to depend on the quality of the context that you provide. However, too much context can prove distracting. So let's consider some automated methods we can use to provide that context. Now, we'll briefly look at 3 different kinds of contextualization strategy. The simplest strategy is simply to include a text window surrounding the cursor. This might work okay if, like in the demo, the entire app is located in a single file. But what if you're in a new file, or one that doesn't include relevant information? Or, perhaps worse, distractingly irrelevant information. And even if there is relevant information in the file, it may be too much to practically include, as time performance scales with the length of the prompt. Although the size of context windows supported by models has been increasing, scaling cost is still significant, and previous research has shown that more is not necessarily better. Vector retrieval, on the other hand, is another common strategy which involves pre-processing the entire code base, dividing it into chunks, which are submitted to a separate embeddings model, which embeds the chunks in a high-dimensional semantic space. You then similarly embed the program chunk and use closeness in this space to select the most relevant chunks, which are then included in the prompt. However, the semantics of this space are deeply associative and opaque and may not correspond closely to or at all the semantics of your programming language. Now, repository-level contextualization, on the other hand, covers a range of emerging approaches to collate cross-file context. In particular, you might consider the imports at the top of the file where the completion is happening, pull in those files, and add them to the prompt. In this way, these methods are beginning to incorporate language-specific semantics into the process. Our method fits here as well. Research in this area has exploded in the last year. What differentiates our method is that we adopt a granular type-focused approach which uses typed holes to connect cursor-local semantic properties to repository-wide semantic context. Our prompting process consists of a 3-part conversation between programmer, the Hazel Language Server, and the language model. The conversation begins by sending the model a language crash course, generic for each completion request. This includes a brief specification of Hazel syntax, a list of input-output examples consisting of program sketches and corresponding fillings. The programmer then designates a program sketch for completion by entering 2 question marks at a typed hole, and the Hazel Language Server augments that sketch with semantic information related to the hole. The LLM then responds with a suggested completion, and if there are any static errors, the language server sends the resulting error messages back to the model, which then replies with an attempted correction. For the sake of time today, we'll focus on our core contribution, the construction of the static contextualization prompt. The idea here is that we use information local to the hole being filled, specifically its inferred type and typing context, to collect relevant type definitions, as well as the headers of any functions or values relevant to constructing or operating on those types. To begin, the programmer opens a file, writes a program sketch, and then they designate a hole for completion by entering question mark, question mark. This prompts the Hazel Language Server to step in. The language server examines the hole, extracts an expected type and typing context using Hazel's bidirectional type system. Putting the typing context aside for the moment, the language server then uses the expected type to extract relevant type definitions from the code base. The language server deconstructs the type, in this case retrieving the model type definition. Similarly, it retrieves the action type definition, and this process continues recursively, retrieving the grid type definition, and finally the emoji type definition. With these relevant values retrieved, we then proceed to extract relevant function and value headers using the typing context. Again, we start with the type of the hole. This time, we'll extract a collection of target types which can be used to construct the expected type. The first target is simply the expected type itself. Since the expected type is a function type, we additionally include its return type as a target, that's model in this case. It may look as if there is no more structure to work with, but if we normalize the expected type, replacing the model type alias with its definition, we see we have a product type which can now be deconstructed. So we add its constituents to the target types. We then consider the target types one by one, filtering the typing context for either values of that type or functions that return that type, or functions whose return values are products containing a target type. Program synthesists in the audience might recognize this as a very simple form of type-directed term enumeration. Here, there are no values of the expected type in our context, so we move on to the next type, model, and retrieve one corresponding header from the context. The next target, grid, also does not occur directly in the context, but there are, however, 3 functions which return grid. We retrieve their headers. Neither of the remaining targets have any values in the context, so we're done. Finally, the expected type, relevant types, relevant headers, and initial program sketch are all concatenated together, creating what is basically a static program slice focused on cursor local semantic context, which is then dispatched to the language model, which finally returns a completion. So how did we evaluate this? Now, it turns out that most current evals in this space consist of single file tasks which are low context, in that they only require built-in or standard data types, making them ill-suited to evaluate static contextualization. Now, there are some emerging repo-level evaluations, but these tend to focus on dynamic languages, such as Python, as seen in the last talk, and these often depend on specific hard-to-port libraries within those ecosystems. Also, these often don't include unit tests and instead use things like lexical edit distance to a reference solution as a proxy to judge correctness. So we ended up creating a new evaluation switch called MVUBench, which consists of a number of self-contained MVU applications which use many custom types and are easy to port across languages, as well as the to-do example we started out with and the emoji painter that we used as a running example. There are a couple others listed there. So yeah, how does this method perform? With no retrieval at all, the model hallucinates constructor names as expected. I want to emphasize that this baseline involves providing only the update function header, just the header, and no additional context. So these zeros should not be surprising. Also, if we just include the relevant function headers alone with no types, this makes little difference. However, when we start to include relevant types, we start to see passing tests. Note that type error correction rounds, which previously had no discernible effect, are now a substantial multiplier. Finally, in the presence of relevant types, the inclusion of function headers has its own large multiplicative effect. Now, we compared our method to a simple vector retrieval baseline, and as you can see, static contextualization performed quite well in comparison. To get an idea as to why, consider this chunk, which is relevant only to the to-do app. This was also retrieved in the context of several other app sketches where it's not actually relevant. This seems to be because it happens to include the string model twice, as well as the string action, making it seem very related on the basis of word association. Now, you can argue the wisdom of using a lot of shadowed names in a code base, but sometimes using certain names is unavoidable. For example, when satisfying a particular module interface, including when using many model view update frameworks. We also compared to exhaustive retrieval, by which I mean sending the entire app code as the prompt. As you can see here, static retrieval performs similarly, though not quite as well, as exhaustive retrieval, but at a significant lower cost in tokens. Since exhaustive retrieval necessarily scales with codebase size, as the codebase gets larger, this suggests static retrieval may become increasingly token efficient. We also ran similar experiments in TypeScript and saw a similar trend, achieving similar overall performance in the maximum context case. There's a lot more details about our TypeScript experiments in the paper. We also reran all of the experiments that we had previously run with GPT-4 with an open source model, the StarCoder 2 model, again, mentioned in the previous talk, which showed roughly similar trends. Now, implementing our method in TypeScript using the existing language server was difficult. This led us to sketch a prospective extension to the language server protocol, which would streamline integrating this method into a wider range of statically typed languages. If you're interested in exploring static contextualization in another language, please find and talk to co-author Jacob. Jacob implemented our TypeScript version and is working on a VS Code extension to expose relevant static context through a VS Code's sidebar. Now, there is a huge amount of activity in this space, mostly in the last year. So please see the paper for detailed comparisons between our methods with all of these and more. But briefly, our distinguishing factor is our use of typed holes to connect inferred semantic information about the negative space of incomplete programs to extract relevant context in a type-directed way. Now, in conclusion, and to talk briefly about future directions, one framing we've been increasingly seeing in this area is the idea of building user interfaces for LLMs, the idea that LLMs need IDEs too. So we're interested in looking We're interested in looking at how work here can interact and cross-pollinate with human factors and editor tooling. In particular, we're interested in broadening the conversational framing we described, making the conversation more dynamically structured. For example, allowing an LLM to request specific information from the language server, or by providing UI scaffolding to help it follow a more complex, multi-stage, type-driven design process. Please come say hi if you're also working in this area, and that's it.
Really, really awesome talk. The main question that I had, and I'll chat more with you offline, but in programming languages like Rust, for instance, you have like a hierarchy of libraries, right? So the standard library has like a bunch of modules. Each of those modules might have like a bunch of types underneath. And for a given type that you're using in your program, usually it's not enough to look at like the particular function that's being called on that type, like method on the type, or even like the documentation for the type itself. But if you go up one level to the module, then you find like all the information that says like, yeah, here's how these types relate to each other, and like all these kind of like cross-cutting things that talk about how to use that module in general. Do you expect that including that sort of like information one level up in the hierarchy would be useful for prompting LLMs? Like, it's not really type information, but it's like prose that links to other types, and then like maybe you could pull those into the context as well. I don't know if that, is it something you have explored, or what are your thoughts on that?
I mean, we haven't specifically explored that, and I'll say I'm not like a Rust person, so like, yeah, I can't comment on the particulars here. But like, yeah, I mean, it's like, I sort of mentioned that like I was looking at what we're doing as like a simple kind of program enumeration thing. So like, I feel like you can take this model definitely further. Like you can go kind of like, you know, more levels of remove from the thing that you're looking for and bring in more context. I mean, like the further you get away from like the concrete expected type, like I guess the higher the odds are that the stuff you're going to pull in is unrelated. And definitely, you know, we had issues with like, yeah, you do want to try and avoid pulling in distracting information. But I mean, I think it is definitely worth trying to like to draw information from a broader scope, and I'd be very interested to talk about that more with you.
Hi, I'm from the Haskell community, so I was wondering, I mean, this looks pretty cool, but I mean, the types are pretty simple, what you show. So I wonder if you have played with, you know, maybe more complex types. Do you think this will scale? Give me some intuition behind that, yeah.
I mean, yeah, hard to say for sure. Like, definitely I'm interested in doing explorations like in a language like Haskell that, yeah, has a much more complicated type system and also has a much more capable language server. It's like, we ended up picking TypeScript for our secondary experiments because, I mean, it's a popular language. People like to see popular languages out there. But insofar as implementing the basic aspects, we certainly would have had an easier time with the Haskell language server. But yeah, I mean, there's definitely like some points of ambiguity as to how this is going to scale to more complex type systems.
All right, thanks.
My question is kind of a variation of the previous one, but specifically, if you're thinking about type complexity, not in terms of the expressivity or richness of the type system itself, but you have maybe a fairly simple type system, but it's just a large code base, and so you have some record type, and it references a lot of types. Those are in other files. That potentially, you said that it is recursive, potentially in this case the tree is quite large, and then in turn each of those referenced types has a bunch of inward pointing, and the arrow going the other way, right, uses, I guess, that could potentially be useful information. So that, we've seen this type of thing be already a pretty significant performance problem just in type checking and inference in production systems like TypeScript and co. What I'm curious about in this case is if you have any thoughts, just from having run this experiment, on what the most useful parts of the graph are for facilitating these completions. So obviously, naively, you could say cut the recursion depth off at like 5, but you might also ask like, what are qualitatively the more useful parts of that?
Well, I mean, I think so far our trees haven't been deep enough to really think qualitatively. Yeah, I mean, like you definitely bring up a good point. I mean, it's like, I think, I mean, in the future, the way prompting processes are going to work is like they're going to have to negotiate between including like many different genres of information, like not just these recursive type definitions too. So yeah, I mean, some people are doing work using machine learning itself to select the information which is relevant. So like, I think that, yeah, I mean, in a general setting, that's probably what you want to have some like complex system which is taking into account all of the information you could theoretically include, and yeah, do some kind of weighting of that info, possibly involving different ML processes.
Cool, thanks.
Yeah, let's thank the speaker again.